Yeah, thank you all. What a pleasure it is to be here, and such an awesome crowd here, and collectively here for one main purpose, and that's to protect our water quality and the environment. So it's just a real pleasure to be able to share what we do and what we're learning too. So we'll go through that here today. So yeah, my name's Chris Stransky, and I'm here with John Rudolph. We're aquatic scientists. We've worked with the GEI. Have been in the field for over 30 years and have been able to see a lot of changes that have happened. We got started back in graduate school working together. So here we are, still working together. And I'd like to point out Kelsey Chung and Sierra Wallace, who are over here. They're part of our team, and they've gotten to know these lakes really well, being out there all the time. And then Olivia Burgess is over here. She's an intern at SAPA, so she's going to be graduating and looking for jobs, by the way. So come and say hi to. She's been awesome. We've really appreciated having her get out to join us on the lakes. I also have the pleasure of, it's been a real honor to serve as the president of an organization called Society of Environmental Toxicology and Chemistry. That's CTAC for all of North America. It's a global organization. And I just gave a talk a couple days ago to our Southern California chapter and put a picture up of our planet with the moon and the Artemis mission and looking at that little blue-white circle surrounded by blackness, and that's what we've got to protect, right? It's amazing. Just imagine being an astronaut, seeing that. It's been real inspiring, but I think that's something that should bring everybody together to say, wow, we've got a job on our hands to protect that little blue planet, because we don't have another one. And so to see everybody here, and everybody get motivated, my job there is to try to get people inspired and excited about the type of work that they do. And I can tell you, we sure are, so we're real proud to be part of this movement here. So thank you guys and everybody that's contributing. We are here to talk a little about the beneficial uses, right? The TMDL that Tess just described. And the purpose is to protect the water quality for recreational use, but also aquatic life. So that's a big job for these lakes. And I'll say I'm real proud, and our team I know is real proud to be a part of this, because we've been monitoring the lakes for over 12 years now. Adam gave a great overview of all of the different things that have happened over the years to increase and change the water quality for Lake Elsinore, starting from reconfiguring the lake to make it smaller, to increase water levels and maintain water levels. If the recycled water wasn't added to the lake right now, it would have been dry a couple years ago just from drought and so forth. So it's a managed lake, and we've seen some tremendous improvements. And I'll have to say, we did some studies a couple years ago, 2022, to look at different treatment technologies in the lake. We did mesocosm studies and tested a bunch. It happened to be during one of the worst blooms. It was extremely challenging to see changes that occurred. One of those tests was with the mole-area units. And later on, Adam got that initial pilot barge going in the lake, and we thought, okay, it's a pretty big lake. I don't know that we're going to see much happening. And he just took the bull and went ahead and got 2 more of those units out there. And here, we've been doing the monitoring all these years, and to be a part of something where we've seen an actual change, despite some skepticism too, to be honest, up front, because we've seen how challenging this lake has been, and the algae blooms that we've seen out there to change. And 2025 really was a banner year. It was one of the best water quality years that the lake has seen. And so that's been really cool for us as a team to be out there doing the monitoring and be a part of that, and looking forward to seeing that water quality continue to improve. So nice job, Adam and the city, for just going for it. And sometimes, you can monitor things to death, but until you actually implement something to see change, that's what we want to see. So pretty excited about that, and John is going to be following up from me on talking about some of the different alternatives to continue to enhance the water quality for both lakes. So that's awesome. So when that surf park gets built, I want to be one of the first ones on there. So Garth might fight me for it, though. We'll see. So anyways. These are real gems, and our staff love to get out there. I mean, there's days out there where you're just amazed by the birds. How was that presentation? Was that awesome? To see all that was super. And again, this is something that you don't really you got to step back and take a look at what you're doing and protecting. And it's really, these are gems that we want to preserve and protect. And so again, it's a real honor to be involved with that. Okay, so I think that's the introduction. We can jump into the next slide there. I guess I have a clicker, but so we've got 3 different topics that we'll talk about here. So the first one is we'll talk about the golden algae issue that we have at Canyon Lake that has popped up. And then I'm going to talk about that, and then John is going to talk about 2 different programs there. One for treatment alternatives for Canyon Lake that is in progress right now, working through that. And then he'll also talk about the LESJWA study. And for Canyon Lake, as you've heard, alum has been applied for the past 12 years approximately, about twice a year. That binds the phosphorus, it removes the nutrients. And that has been a success story for the lake. It's really seen a change in the water quality, better clarity, no more algae, cyanotoxin blooms to a limited extent and without problems with the fish have been healthy and so forth. And now we have something that's popped up that I will talk about here with golden algae. But there's been a success story with regard to the treatment. Now we have to look at what are those alternatives moving forward. And then there's the LESJWA alternative study that stands for Lake Elsinore Aeration and Mixing System. That was installed in 2007 in the lake to add air lines to the lake and also some mixing pumps that circulate the water, bring oxygen down to the lake, reduce the phosphorus that comes up from the sediments to increase the water quality within the lake. And that's had some success too, and it's been in place, like I said, since 2007, but it's becoming near its end as far as how effective it's been. And so some alternatives need to be evaluated to enhance the success of that system, but now taking into account the current systems, the mole air units that are out there as well. So that's all part of the picture now as we've seen success with regard to that. So that's great. So we can move on to the next slide, or I guess I can point it that way. So I'm going to talk about the golden algae issue. Love talking about the positive stories, but here's one that's a new challenge that we do have that's facing us. So this is a species of algae that is neurotoxic to fish. We don't think it's a problem for humans, really, that anybody has documented. So it's really a fish toxin. It actually causes them to act strange in behavior. They can sense it and they can swim away. It's particularly, not only does it produce a toxin, but it actually physically can attack the fish. They'll surround the fish. They have a little flagella and they move around. So it's really a mean little algae species. It was documented really in the 80s in Arizona and Texas, and then was documented first time really in California, not far away in a couple lakes, Mission Viejo and up in Yorba Linda. And it's been in those lakes in Mission Viejo. They've been battling it for over 10 years now. They first found it in 2014 and have had challenges getting rid of it out there. So they're still having challenges keeping fish alive. It was documented in Lake Elsinore in 2018. That was right after the Holy Fire and the flooding that occurred. We did some presentations on that. The water quality in the lake changed rapidly, and soon after, there was a big fish die-off in the winter, which is odd. We never see that during the winter, and attributed it to the golden algae. For whatever reason, it decided to bloom, but it has never come back in Lake Elsinore at this point in time, so that's good news. But it was first noticed in Canyon Lake. A fish die-off happened last April, a massive fish die-off throughout the lake. And the water color kind of changed from a greenish color to a brown color pretty quickly. We got out there quickly, took water samples, and found the golden algae in Canyon Lake. So that was a new finding for the very first time. So a few things about what we know. Obviously, it is toxic to fish. There had been a fish kill up in Menifee Lakes back in 2014 as well that was attributed to golden algae too, so it was up there as well. The water quality conditions in Canyon Lake are a little bit different than what they have been. We've seen an increase in pH, a little bit of increased TDS and conductivity in the eastern part of the bay there as well. And so we're trying to understand what is it that caused this to trigger. The phosphorus concentrations, again, the alum has been very successful removing and reducing the phosphorus nutrient concentrations. And they've stayed steady and lower, particularly the past couple of years, which is good news. But there's some indication now that the golden algae actually can outcompete at lower nutrient concentrations. So the question is, what's going to be the proper treatment for something to keep the golden algae from coming? We still have a lot of learning to do here, but I'm going to show a little bit more in a couple slides. And then what is being evaluated? We have to understand the water quality conditions that have triggered the bloom and how we can abate it. And if we're going to implement new technologies, how are we going to make sure that those technologies don't do something that also cause the golden algae to bloom? Okay, so next slide. There's monitoring that's been done. As you heard from Tess, there's a TMDL monitoring program to get out there regularly. There's 4 places in Canyon Lake that are monitored. And focusing on sites 8 and 10, there are 2 locations. One is in the main basin, and then that's site 8, and then site 10 is in the east basin. What we have noticed, what has happened is since that fish kill that happened in last April, it did go away. The algae does not like warmer water, so during the summer it went away. And then we thought, okay, that's great, let's hope it doesn't, but it did come back. In October, it came back pretty quickly. So a decision collectively was made to go ahead and add an algicide to the lake to knock it down and try to prevent another massive fish kill. That was successful, it did. We knew this was a temporary treatment, there was no fish kill. The water cleared up, and so that was encouraging. But about a little over a month or 2 later, it started to bloom again in the east part of the bay. So we started to see that algae come back. And then that was in around December. And it's been that way for about 4 or 5 months. It's stayed in the east basin, and we're taking samples, taking them to a lab, they're identifying them, measuring them, and giving us a species ID. And we've also been taking subsamples and bringing them to a lab and documenting whether or not it's toxic to fish in a laboratory, and we've seen that. And then just a few weeks ago, that algae has bloomed now in the main basin. So that was, unfortunate for us to see. We were hoping it wouldn't, transition to the other part of the basin. But what we're looking at is the differences in the water quality between the east basin and main basin. The east basin has had higher pH, a little bit higher conductivity. There is Salt Creek that comes in from above, and it's shallower too, so it gets stirred up more. And these algae create these cysts that will sit on the bottom. And if they get they're pretty resistant too, so if they get stirred up into the water column, they could be forming blooms as well from that as well. So we're trying to understand what the water quality parameters that are triggering this algae and the differences between the 2 basins there that we've seen. Okay, next slide. I mentioned toxicity testing, so we've been taking samples, bringing them to a laboratory. Actually, that we had been involved with building and running labs in our past lives too. And this is where you take a little fish. This is called a fathead minnow. It's 4 to 7 days old. We put them in the sample and just look at survival over a 96-hour period. And it's real simple. Does it live or die? And what we're finding is a very strong correlation between the cell density of golden algae and mortality of this little fish in the laboratory, and that has corresponded with some fish, dying in the lake as well. And I should point out that right now there is sporadic mortalities of fish being noted in the lake, but not a widespread kill. So anyway, this is also important because the golden algae doesn't always produce a toxin, and the toxin can vary depending on the conditions. So this is a more confirmatory method to address whether or not we have toxic water in the lake. Okay, so next slide. So we see a response right around 2,000 to 3,000 cells per mil is when we start to see a pretty quick drop off in survival. So the data collected to date, we've tried to understand why is there a difference between the east basin, west basin, and main basin? Why was the bloom staying in that east basin? We had much higher pH. It does seem to favor pH, but it could be producing elevated pH because it's respiring, so it's kind of a positive feedback loop. But studies have found that increased pH can increase the toxicity. We know the algae does like elevated conductivity, so that's one thing. It was a little bit elevated in the east basin as well, and we saw more stirred up sediments and so forth as well. So we've done some correlations to look at what might be causing the relationships that we've been seeing. So we're trying to understand again what might be causing it, so we can figure out treatment-wise what's going to be the best approach moving forward. Okay, and next slide. We did take in January a couple samples from the lake and brought them to the lab and had this question of, is this bloom dependent on the nutrient concentrations or not? So as I mentioned, the nutrient concentrations, phosphorus has been lower in the lake because of the alum treatments, which has been great. We took water samples that were toxic from the east basin and non-toxic from the main basin. We did this experiment where we added nutrients to half of them and left the other half alone. And the sample that was toxic with high golden algae in the east basin transitioned pretty quickly to a green algae kind of culture that was non-toxic actually after just a couple days. So it showed that the golden algae was outcompeted when we added some nutrients to the water. We were able to repeat this twice, And literature has also found out that this is the case. So now we're dealing with a real challenge because we have an algae species that likes lower nutrients. Here, all this time, we've been working to bring the nutrients down to prevent cyanobacteria blooms. So this is a real unique challenge. So we've got to figure out what the right balance is and how to stop this guy. Okay, next slide. And I have confidence we can do this. We just got to understand this better too. So I don't want this to be too doom, go back to all the positive things that we've seen and the progress that's been made, and I'm real confident we can get there. But we got to understand this particular algae better. So in summary, we've learned a little bit more about it. We do have some ideas on some more studies that we suggest might be done before we select a final alternative for treatment and move forward with that. So I'm glad to take questions on the golden algae if we want to do that, or we can wait till the end. John is going to actually jump in and talk about the different treatment alternatives for both of the lakes. There's some things that we don't know about this algae. It's been out there for a long time, we know. So, and it was found, like I said, up in Menifee Lakes. Actually, I didn't mention that. A sample just collected recently did find the golden algae up in Menifee Lakes. So it is something that's up there as well right now. It's not connected, as far as I know. I don't think there's flow right now coming into Canyon Lake, but it's also another source that we need to be keeping an eye on. With regard to Lake Elsinore, it's shallower. It does get stirred up for sure. There's probably spores that are out there in the sediments because there's already been bloom that happened. But again, there hasn't been a resurgence of it. We think that it's probably just a combination of it can't compete against the existing algae species that are there, to be honest, and it just hasn't been able to take hold. So we want to understand that better, right? So good question, yeah. So there are plans to look at sediment for a couple of reasons. One of them, the primary one, is to go back and look at sediment oxygen demand to find out, how much oxygen should be, potentially added to the lakes to reduce the phosphorus and nutrients from the internal loading. So that's one thing we want to look at. And we did do a study like that for Lake Elsinore to sort of gauge the size of the systems, how much oxygen should be added to Lake Elsinore. With regard to the golden algae and the spores, that is something that we've thrown out as a potential idea, try to get some sediments from the East Basin, maybe in the main basin, and look at the surface of those sediments and see if there are viable spores there. And if they do get kicked up, could they cause a bloom? We don't know the answer to that. Maybe the main basin is deep enough and it's anoxic that they do die, but we've been told that the spores can even resist being desiccated, and so these are tough spores. And we get into some pretty academic research like that, but we've worked and we're partnering with USC, Dave Caron, and others that could help us, really try to get to some of these questions that are going to be challenging to answer for sure, but that is an important question. So, yeah, so that is a concern, right? So they sure could, and because these golden algae do find a way to attack the fish and get onto their gills and so forth, you can imagine a bird grabbing that fish and taking it somewhere. And so very well being that even the birds could transport the golden algae somewhere else too. So it's kind of like the mussel issue too, same thing where, your natural species out there can move things around as well. So yeah, that's a concern for sure. Yeah, it's probably not in forever, I don't know, perpetuity. Yeah, I don't know without, there's only so much literature out there on this right now, and I think that's another area of study, like how long and what conditions can be used to kill these spores, So, maybe there's adding something that settles to the sediments is something that could be entertained that could kill the spores. We don't have an answer to that right now. But yeah, there's a lot that we don't know specifically about them. So that's kind of where we're focusing now, a little bit more on the water quality conditions that it can tolerate. I also kind of skipped and missed this part, but we shouldn't be seeing the golden algae at the temperatures that we're seeing right now in the lake and the conductivity, because it seems that it has adapted to these conditions. It generally likes cooler temperatures and higher salinity than what we are seeing in Canyon Lake. So that's just another factor. So we really got to understand, what's making these guys tick for sure. But the spores is an issue. There's a lot of uncertainty about those. Yeah. And that's common for all algae species, a lot of algae species. A lot of algae species create spores. And there's still a mystery of blooms offshore, right? And when they come and go, why? And well, for something triggers those spores at some point to bloom. So, yeah, an immediate trigger or something. That's a great question. You know, there have been fires that have really affected water quality around that time frame. Back in 2014, I'd have to go back to look exactly whether or not something like that triggered a quick change in the pH or something else that allowed it to bloom. But that's, you know, something to look at. That's an interesting lake, and the fact that they bring in highly treated RO water, and so it's got really low conductivity and it's pretty clean water, really low nutrients as well. So they've had some challenges there. They have noticed that when it rains and when they get more turbidity and nutrients, the golden algae tends to die back, and they can keep fish alive in the lake too. So they're so they're working on a system. They actually have pretty high salinity in that lake too, so that's probably making it a little bit worse for them. They have just naturally higher conductivity to deal with. Yeah. If no other questions, we can chat more at the end too, but I want to give John some time here because he's got more slides than I do. So anyways, but it's real interesting, you know, like to go through the different treatment alternatives. So I'm going to hand the mic over to John, and glad to entertain more questions afterwards. Thank you, guys. Yeah. I'll just hang over here.
But we thought it was important when we were putting this together that we go ahead and address the golden algae issue first, right up at the front, because you know, obviously we want to talk about this big elephant in the room, right? And everybody knows what's going on in Canyon Lake. Address this because the stuff that I'm going to be talking about now on the next, you know, few slides is all about, okay, how do we move forward now? And golden algae needs to be a part of that solution. You know, it's kind of thrown, if you will, a monkey wrench into kind of the plans that we had moving forward, because it has these different characteristics than any of the other types of algae that we have been dealing with historically. You know, just typical beneficial green algae or the cyanobacteria. They prefer warmer water and higher nutrients, versus golden algae is the opposite of that, colder water and lower nutrients. Okay, now we got to figure out how does this work into the plans that we have moving forward. And so Tess kind of set us up a little bit as far as moving forward. I'm going to be talking specifically about stuff regarding to Task 4 of the revised TMDL and Task 5. So Canyon Lake and Lake Elsinore successively here. But again, we thought it was important to talk about golden algae first because we have to strike this balance now with Canyon Lake. I'll start off with Canyon Lake and then go to Lake Elsinore at the end. But we have to strike this balance now. Okay, we've got these two different competing algae that have different characteristics, competing characteristics really. How do we deal with that? So moving forward, we're going to have to figure this out, because ultimately, long term, we need to know we're trying to, you know, prevent these blooms like this because we want a more holistic whole lake solution. We're dealing with, you know, different beneficial uses, either it's recreational or, you know, fisheries, or just it's a drinking water reservoir, obviously, so we have to, you know, take that into account as well. So there's lots of things we have to take into account here for Canyon Lake. And ultimately, like Chris mentioned, we know, you know, we want to reduce these short-term solutions. We need to be looking more long-term, right? How is this lake going to look in 5 years, 10 years, 20 years down the road? Come up with solutions that are looking further out than just a short-term algicide application. We can't just keep applying these short-term solutions because we know they're short-term, just Band-Aid fix. We knew the algae was going to come back at some point after the bloom and the algicide we had last November, but, you know, we were trying to prevent a big fish kill at the time, so we had to do something at the time. So anyway, we need to reduce the need for short-term solutions and look more long-term. And that's what these ultimately solutions, Task 4 and Task 5, are geared towards. Okay, so what's the objective of the offset program? So, you know, there's two different ways you can deal with nutrients. You can either deal with them up in the watershed via structural BMPs or some other way, or you can deal with them in lake. And so what I'm going to be talking about is more about the in-lake solutions. How are we going to perform some sort of offset program to reduce phosphorus in the lake, right? And so that has to do with alum, and we've talked about a lot already. We've been doing that since 2013, and I'll show you a slide here in a little bit to kind of show the success story that alum has had in Canyon Lake to reduce phosphorus and overall algal biomass. And so to get to that, there's lots of ways in lake solutions that you can get. There's not just one solution that can be used, or maybe it's a combination of solutions that you need to look at. And so part of this Task 4 is to look at various alternatives in addition to, or maybe instead of, the alum program. So what we're doing is we're evaluating currently a list of 17 different in-lake treatment alternatives to reduce nutrient load to Canyon Lake. And so This is a former list that was brought up. We've already gone through this process with Lake Elsinore, which I'll talk about here next, and come up with a solution for that. But we're going through the same list again. This is a list that was put together of in-lake treatment alternatives by Dr. Alex Horn, UC Berkeley, who's worked on Lake Elsinore for a long, long time, and many other lakes in California dealing with similar issues. And so we're going to be going through a series of special studies to figure out, okay, once we do come up with a solution, perform some special studies to kind of dial those in a bit further and ultimately come up with, you know, what's the best either one treatment or combination of treatments for Canyon Lake to put in place to help offset some of the phosphorus credits that we need for that lake to help reduce algal blooms in the lake to prevent, you know, to preserve all of our beneficial uses there. And so I'll show you the list of 17 when we get down to Lake Elsinore, but in the interest of time here, we borrowed down the 17 solution or 17 in-lake treatment alternatives down to 6. And so we go through an initial screening process, which basically just says, okay, what's just a no-go from the start? And we can just rule it out. We did that, and going through that initial process of screening, we got it down to these 6. Now, in no way are these in order of priority. This is just a list, and you'll see on the next couple of slides, these are for discussion purposes only. There's a lot more study that needs to go on about these different treatment alternatives to decide, okay, which one are we actually going to move forward with? There's, you know, and I'll go through some criteria that we use to figure out, okay, how do we get to that bottom line of which one's going to be the best one to move forward with? But ultimately, when you're dealing with Canyon Lake, it's a much different lake than Lake Elsinore. Even though we're going through the same 17 in-lake treatment alternatives, you know, we're dealing with different hydrodynamics. It's a much smaller lake. It's a much deeper lake. And in fact, Canyon Lake almost operates like 2 different lakes. You've got the East Bay, which is shallow, not much circulation. You've got the Main Bay, which is much deeper and larger. And they kind of operate almost independently of one another, even though they're hydrologically connected by a small tunnel between the two. They operate differently. So we have to come up with a different solution for Canyon Lake than we did for Lake Elsinore because it operates quite differently. We also have to think, well, this is a drinking water reservoir. You know, it's for municipal use as well. So we have to come up with different solutions for that than Lake Elsinore, which is not a drinking water reservoir. We already know, you know, some of the sources there, urban, ag, external sources, but we also know that we have internal sources. With any lake, you know, there's both external and internal sources of nutrients. Internal sources of nutrients are that come from the sediment that get recycled on an annual basis. You have algal blooms, which start in eutrophic lakes anyway. You have algal blooms in the summertime. Those algal blooms start to die off in the winter. All of those algal cells fall to the bottom, release their nutrients, get back incorporated into the sediment. Then the next year comes around, the sediments release their phosphorus, algal bloom starts again. So it's just an internal recycling of nutrients over time. And for Canyon Lake, it's a much different scenario than we're dealing with Lake Elsinore. In Lake Elsinore, the internal sources of nutrients account for about 75% of the overall load. When you look at Canyon Lake, it's almost the opposite of that. It's about 25% of the overall load to Canyon Lake comes from internal sources, where about 75% is external loading from the San Jacinto River and Salt Creek from the east. So again, quite different system. It's going to need a different solution, and maybe even a combination of solutions for these in-lake treatment alternatives. I'm going to be talking through quickly each of these alternatives for Canyon Lake, and not really advocating for any one of them, just kind of talking through the various points, pros and cons of these. So the first one will be dredging. Now, there was a dredging operation which happened in Canyon Lake from 2004 to 2006 or so. Didn't remove a whole lot. It started in the East Bay, and they were stopped at some point. The process was stopped, and the dredging actually wasn't completed. But this is an alternative. You know, we know that Canyon Lake over time it fills up about 2 to 3 centimeters per year or so of just sediment loads coming down, adding to the sediment on the bottom. And so at some point, you know, if it's not part of this process down the road, Canyon Lake is going to need to be dredged because it's losing storage capacity. As the sediment fills, the water storage capacity becomes less, and you get more sediment disturbance and all of that. Eventually, if it's not part of this process, it's going to have to be dredged anyway. But as far as the dredging process for this task 4 alternative in-lake compliance, it would be dredging the East Bay only. That's the shallowest portion. It gets down to about 6 feet deep, maybe on the eastern portion, and maybe up to about 12 to 14 feet on the eastern portion, or I'm sorry, the western portion of it, focusing on the top 2 feet of the sediment, that's where a lot of the nutrients are. If we were to remove that top part of the sediment from the lake, you're removing a lot of that internal loading, and a lot of it, that 25% would be reduced to much less. Maybe not 0, but much less than it would be otherwise. So this would be about 2,000 cubic yards of sediment that were removed. It's an expensive solution. We're talking somewhere north of about $20 million to dredge just the East Bay alone. There's lots of things to talk about. There's disposal, big part. Where are you going to put that sediment? You can't just dredge it. You got to have somewhere to put it. Lots of testing. Is it contaminated? Doesn't need to be dealt with in that way. Then if it is contaminated, it gets dealt with in a different way, rather than just like a reuse type scenario. Ongoing maintenance, there's really nothing, right? Once you dredge, okay, the dredge is over with. So there's nothing to deal with there. But like I said, you're reducing that sediment, internal sediment load by reducing that sediment nutrient reservoir at the bottom of the lake that just gets recycled year after year after year. And another potential benefit, as Chris was just talking about, the cysts that the golden algae go to when they go into their dormant state, maybe during the summer when they day off, it's down in the sediment. So you're actually potentially removing a lot of that cyst load as well. So a couple of benefits there. Next one, hypolimnetic withdrawal. So the hypolimnion part of the lake, this is a term that basically describes the bottom portion of the lake. The lake stratifies during the summer, thermally stratifies. So you get the upper part that's called the epilimnion, which is the warmer part, and you get the bottom layer, which is colder. It's called the hypolimnion, and you've got the thermocline kind of in between the two. So the lake thermally stratifies, and there's no mixing really between the two during these summer periods when you get lake stratification, and you get this really low DO at the bottom of the lake. And when you have a really low DO at the bottom of the lake, that actually facilitates nutrient flux, as Tess mentioned, flux from the sediment, right? You get nutrients coming out of the sediment. And that low DO actually makes that go faster. So, and I'll talk about oxygenation as an alternative to that here in a little bit. But hypolimnetic withdrawal, what it would mean is you're taking that water, that high nutrient, low dissolved oxygen from the water. And in this case, we did a little schematic here to kind of show you what it would look like. Taking water from the main basin has a strong stratification during the summer, and pumping that water to the far end of the east basin, and then letting it flow back over time. And during that process, while it's being transferred, you can treat it. So you can remove the nutrients either through some sort of ACH, like aluminum chlorohydrate, which again bind the phosphorus up, or alum, or some other sort of phosphorus sequestration technology, as well as aerate it. So you're taking nutrient-rich laden water from the main basin, taking the nutrients out and dumping it into East Bay. So it's just on this constant recycling system. And so by doing this, you can either pump it overland or even underwater. I've heard of lakes that use an underwater piping system that just transfers, so you don't really see anything, right? Everything's underwater. So this is one of the other alternatives that's potentially being considered. Okay, the third one is dilution with RO. So we know that the population in this area is increasing. EVMWD has a treatment plant. This is going to have to be ramped up over time, right? So they're going to have more and more recycled water that's gets generated as the population of this area increases. Now this was a study done by Kennedy Jenks, another consulting firm, back in 2017, where this was kind of mapped out. Okay, what would this look like? If we have some excess water, there's about, as mentioned earlier, 6 million gallons a day of treated, recycled water goes into Canyon Lake, goes into Lake Elsinore. Well, as the population increases, there's going to be more and more of this water. So any of the excess can therefore go somewhere else. You can either go into the back basin to be infiltrate for groundwater, but the other alternative was this one, where we thought, well, what if we just take that water, recycled RO water, and pump it into Canyon Lake for potable reuse, indirect potable reuse. And so that was the thought here. If you're taking that water that's treated, low nutrients, RO water, and pump it into Canyon Lake, and there's a couple of different advantages here. One is that it's a recycled, indirect potable reuse, which is one of the big, again, one water, reusing our water over time in this drought, stricken area. But there's also this issue, okay, well, there's a regulation, Department of Drinking Water. It's got to be in the lake for at least 60 days before it can be used because of the indirect potable reuse. It's got to have this hydrologic retention time of about 60 days. Well, we're well beyond that. We did some modeling. It would be about, if we pumped it into the main basin, it would be about 980 days it would take to recycle that, versus East Bay would be about 160 days. So we're well beyond any sort of drinking water regulation for that. But the additional benefit, as Chris mentioned, golden algae, like slightly brackish to marine waters, saline waters, obviously pumping in low dissolved or low TDS water into Canyon Lake is going to lower the TDS, lower the salinity of the lake, which is going to make it less hospitable to golden algae. So there's an additional benefit here too. Regarding the golden algae bloom that we've had. And so I'm going through these rather quickly, kind of a high level. We can talk about it more later if you'd like. Oxygenation. So this has been talked about a lot already. There are a couple of different things we could do here with Canyon Lake as an in-lake treatment alternative. There could be called PACE LOX. LOX stands for liquid oxygen. And so this is a part of the hypoluminetic oxygenation system where you're pumping in basically pure oxygen into the lake bottom to help facilitate that, or to suppress that nutrient flux from the sediment. So if you get rid of that anoxic layer when the lake stratifies and you get that really low DO at the bottom, by pumping in oxygen you're getting rid of that and thereby reducing the nutrient flux from the sediment by keeping the elevated oxygen at the sediment water interface. You can do that lots of different ways. One is through that hypoluminetic oxygenation system, which is the PACE LOX, or the Moliere system like we've been talking about already. It's working on Lake Elsinore. This could be tried on Canyon Lake as well. By pumping that into the deeper areas of the lake where there's a really deep, low DO, it's essentially doing the same thing but in a different way. So oxygenation overall. This does a couple different things. I've kind of talked about this already. When you get that really low DO there, you're helping to increase that DO in the bottom layers to reduce nutrient flux. But you're also aiding nitrification. Now nitrification is taking total nitrogen and breaking it down into ammonia to nitrate over time, and eventually into atmospheric nitrogen, which would gas off. Oxygen is needed as part of that process. So by increasing the oxygen in the lake, you can facilitate the denitrification of the nutrients in the sediment. So not only are you helping to suppress phosphorus flux, but you're also helping to break down the nitrogen cycle quicker. Chemical sequestration. So we've talked about this a lot. This is alum. That's what alum does, right? It sequesters phosphorus so that it's not bioavailable and the algae can't take advantage of it. So, but alum is just one way to do that. There's lots of different types of technologies you can do out there. There's a table up there on the upper right that you can see that talks about some of these things. Aluminum, that will be alum. Lanthanum is another way to do it. So currently what we're doing right now is the routine low dose surface application with aluminum. That's alum. That's currently what we're doing, but there's also future options. We could do long-term sediment treatment where you're providing a kind of a larger dose of either alum or some other lanthanum or some other treatment technology to kind of cap the sediment to help reduce phosphorus flux there. There's also ways you can look at maybe a drip system, which is at this bottom graph here of Canyon Lake. By strategically placing drip systems during stormwater, as the stormwater, the nutrient-laden stormwater is coming in, by dripping that with some sort of lanthanum or some sort of ACH, which is aluminum chlorohydrate, sequester all the phosphorus as it's coming into the lake. Or recirculated water, which is the one I mentioned earlier, taking that hypoluminetic water, treating it on its way to East Bay. So there's a few different ways you can do this to help, again, reduce the phosphorus flux or phosphorus content in the lake. Oh, and I wanted to show this. So this is kind of related to the alum. This is showing the long-term phosphorus concentrations and chlorophyll concentrations in Canyon Lake. And I believe this is so it's showing the main basin, which is in blue, and the East Basin. So this goes back all the way to 2001. And what you'll see is the kind of the lighter blue line in the middle is when the alum program started. So you'll see a lot of variability. Each one of these points along here is an individual sample. So you'll see some spikes, during storm seasons when you have the big flux of stormwater comes in, sediment laden. You'll see a spike even after the alum treatments. But what you notice overall is you'll see that if you just take kind of the average, right, it's come way down. Phosphorus came down first, and then you see chlorophyll start to come down after that, which is, it's a feedback loop on itself. And so the alum program has been very successful in doing what it's supposed to do: reduce reduce phosphorus in the lake, which then, feedback loop reduces the chlorophyll, which is a surrogate for just kind of overall algal biomass. So very successful program there. But I want to show you this because this has been working and has been a proven success in Canyon Lake. And so we're going to be doing a couple of special studies. Tess mentioned this a little bit during her talk about if we're going to be moving forward with some sort of treatment system, whether it's alum, more alum along the way, or some other treatment, we need to evaluate this. So one of the things we wanted to go back and do was there was a effectiveness study done in 2013. If you were to add alum to a lake, how much phosphorus can you actually suppress by having a sediment cap on there? Okay, this study was done, and that's how they're able to calculate the offset credits. By adding so much alum, you can kind of, by that, gauge, well, how much phosphorus is actually removing from the lake. Okay, so those studies were done back in 2013. We want to redo that now. So what were we now? We're 13 years later, right? So we need to redo that study. It was a little bit variable back in 2013. We want to tighten that up, do a better study design, and dial that in so we can get a better, more accurate calculation of how much phosphorus are we actually removing by these alum treatments. And the other thing is, the big concern is, okay, well, if you're adding alum to the lake, which is adding aluminum to the lake, are you going to cause toxicity to the zooplankton? Is it toxic to the zooplankton? Is it toxic to the fish? And so those studies were done back in 2014. We're going to redo those again at various different and even higher concentrations of alum, as well as tested over different pHs. I think it was tested at 1 pH back in 2013. We want to test it at maybe 3 or 4 different pHs, because aluminum can be more or less toxic depending on the pH of the water that it's in. Finally, I talked with a few of you earlier about this. We're going to update the bathymetry map. This is one of the other things we need to move forward in the next couple of years. The lake's filling up. How much water do we actually have there? How much water do we need to treat when you're doing alum or some sort of other treatment process? Well, we want to update the bathymetry there and also look at the organic sediment. Where is really the nutrient load part of that sediment? How deep is it? Is it 2 feet? Is it more? Maybe is it 3 feet now? We need to update that. And finally, as we've been talking about, update this all based on the new monkey wrench that we have of golden algae. Okay, finally, and I think this is the most fun part, fishery management. And so we can use biomanipulation, not necessarily to reduce phosphorus loads in the sediment, but to reduce algal biomass. And this is something that's been done in a lot of lakes across the US, looking at what's called a top-down approach. So by adding the top fish up there, you see on the top we have a largemouth bass, and we've got something called a wiper, which is a hybrid striper. It's actually used in Lake Elsinore right now, I believe, yeah. And so by adding these piscivorous means they eat other fish, add them to the lake, you can start to reduce the next level down, which is shad, and that's the Mississippi silverside, which is one of the most dominant kind of smaller fish here in this area for lakes, because those two fish, the shad and the silverside, eat zooplankton. And what does zooplankton eat? Zooplankton eat algae. So if you have a lot of these shad and silversides in the lake that are gobbling up all your zooplankton, that just leaves free rein for your phytoplankton, your algae, to go crazy. So you want to increase your zooplankton population. The only way to really do that is to decrease the population of these shad and silversides. So by top down, you're increasing your predators, reduces the shad, which increases the zooplankton population. And we saw that in Lake Elsinore. We had this blossom, this big boom of zooplankton. The lake cleared up in about a week, right? It was like it went from maybe 20 centimeters of visibility up to like 4 meters of visibility within a course of a couple weeks, because the zooplankton just went crazy. So this is one of the other potential long-term in-lake treatments that we're thinking about for Canyon Lake as well. And so this is just kind of like next steps, kind of a summary slide. At this time, we're in the process of further taking a more detailed look at those 6 different ones and coming up with a final recommendation moving forward. To refine the process of looking at this golden algae, like Chris mentioned, we're working with Dr. Dave Caron at USC. He's one of the foremost harmful algal bloom experts in California. We've got him on board on contract to help us kind of make some decisions and think through the process here. And finally, again, TMDL Test 4. That's what all this is being driven by. Review and authorize any sort of the in-lake existing treatments, alum or otherwise, and then move forward with these various alternatives, which I just kind of went over all. That's all part of this, and will be, in the next couple of years, thought through, generating reports, all out for public comment. And you guys will be able to see kind of how all this process works here in the near future. So I think that was my last slide on Canyon Lake. Yeah, so maybe I'll stop there real quick. We have time for maybe a couple of questions before I move on to Lake Elsinore. We're pretty sure they are. We have taken some zooplankton samples. This is something that Chris has been talking about recently a lot. We're looking at to see whether or not zooplankton are affected by the golden algae toxin as well. From what I understand, it's really anything with gills can be affected by this specific toxin. And unfortunately, it's kind of interesting because there is no published recommended method to measure the toxin directly. So I can't, for example, cyanotoxins, I can go out and measure microcystin. I can go out and measure cylindrospermopsin, which are 2 toxins in the water, just like any other chemical. Permethrin, which is the toxin that golden algae produces, you can't measure chemically. So the way to measure whether the permethrins in the water, the toxins in the water, is do these fish tests. Do your fish die or don't they die, right? And so that's the way to do it. But it's attacking the gills so that the oxygen cannot transfer over the gill. So there might be really high oxygen, 10, 12 milligrams per liter oxygen in the water, but your fish are gasping for air, gasping for oxygen because their gills are not working anymore. So it probably is affecting zooplankton as well. And I forgot to mention in my fishery management slide, obviously we can't be adding fish if golden algae is going to kill them, within a week of them being in there. So we've got to solve this golden algae problem first before we start down that fishery management pathway. These are the list of the 17 in-lake treatment alternatives that we went through for Lake Elsinore, and they're also being looked at for Canyon Lake as well, although we've narrowed it down to 6 for Canyon Lake. So the ones that are in blue that you see here, those are the ones that were just ruled off during the initial screening process. It's just not viable for Lake Elsinore, whether the lake is too big, it's too costly, whatever it might be. The ones you see in yellow, those are the ones that were already currently going on before we even went through this process. So lake level stabilization, we mentioned we have EVMWD is dumping 6 million gallons of treated water into the lake every day. The lake surface area was shrunk to help deepen the lake, right? Those are two ways to stabilize the lake. That had already happened. Fishery management. There was a big carp removal project back in 2005, 2006 to remove a lot of carp from the lake, which caused problems. They stir up the sediment, they cause nutrient flux. And also adding things like wipers, as I mentioned, these other striped bass to help maintain the zooplankton population. But the one that was, ultimately when we came down to it, the one that was chosen was oxygenation, because this was the only one that was really viable to help suppress that nutrient flux. So let's move on to the next slide from there. And so everything else I'm going to be talking about now is about oxygenation systems and how we got to where we are today. And so there's three things you got to consider when you're talking about oxygenation. The first one is, are you going to make your own oxygen, or are you going to have it trucked in by liquid oxygen? So that's the first decision. The second decision is, okay, how are you going to get that oxygen into the water? And then the final thing is, well, how are you going to get that water to the lake? So there's three different things. There's the type of oxygen, there's dissolution of the O2, and then there's the distribution of that. And so we'll talk about those in sequence here. Okay, so the first one, generation versus liquid oxygen. So these are the tanks you see on the left. This is liquid oxygen will be delivered daily or frequently to these large tanks that you see here. And they figured we would need about 2 tanks, about 6 foot diameter, about 15 foot tall. This would be replaced on a regular basis as it gets used up. Versus the other side you see over there, these are the oxygen generation systems. They're called pressure swing absorption, or PSA for short. They just take just regular air, right? And then they concentrate the oxygen out of it, extract it, and then that gets used, as was talked about earlier. I think you were talking about that, Adam, right? Yeah, about how these systems are on the barges currently that are on Lake Elsinore right now. And they get injected. These are much smaller systems, but very energy intensive as well. So that's the first decision to make. The second decision is the dissolution. So how are you going to get that oxygen now into the water? And there's lots of different technologies out there you could use. These are just 4 of the ones that we thought were the most prevalent or most promising. One's called the Spies cone. That's been around for a long time. It's been used across the US. It's probably the most, it's the technology that's been demonstrated the most to work, I guess. There's oxygen saturation technology system, OST systems. There's a blue-green high-pressure system. There's the Moliere system, which we talked about extensively already. These are just 4 different examples of things that could be used to get the oxygen into the water. Now, Adam mentioned this earlier also. The 15,000 pounds of oxygen per day that we need for the lake, that was determined by a study that we did back in the summer of 2024, I believe it was, as part of this whole process. We took some sediments from the lake, took them into the lab. How much oxygen does that sediment actually consume, either through chemical means or through biological means? Does it use up oxygen quickly? And we figured, take this small-scale lab study and extrapolate to the lake. The lake needs about 15,000 pounds of oxygen per day to make sure that it stays oxic, top to bottom. Okay, so that's how that number came up with. And all these systems are going to be used to help fulfill that requirement for the lake. And so part of the dissolution, okay, once we've gone through those different technologies, there's, okay, the other part of that is, well, how are you going to actually get it out to the system? So there's 5 different ways that we considered here. One was a shore-based system. So all that, whether it's a Spies cone or an OST system, whatever, it's on shore and just pumps oxygen out to the lake via pipe. The second one, you have the same thing, but it's submerged. Different way to do that. Or you can have what's called a crib, which is basically just a structure that's out in the lake that is elevated above the lake, and you have your system sitting on top of it. You have a Spies cone on top, or your OST system's on top of that, and it recycles the water either through a single stream, or there's a different way. The blue and green technology does a 2-stream, what's called a high pressure system and a lower pressure system that mix to create a dissolved oxygen to the lake. And then finally the floating barge system, which is what's currently on the lake now with the Moliere system. Okay, so that was the dissolution, getting the oxygen into the water. Now there's the distribution part of that. You can either do it via jet, so it's basically a single pipe which jets it out into the lake, either surface or mid-column or at the bottom, wherever you kind of position it, or what's called a spoke system. And that's eventually, as spoiler, we ended up going with that because it was a much more efficient way to get oxygen out to spread to a larger part of the lake. And you'll notice in that figure over to the right there, the spoke system that we got is fairly large, but the only thing that you would see above it would be the crib, which is a concrete structure above the water. All the rest of that would be below the water. The water gets sucked into the middle, goes up into those arms, oxygen gets injected into it, and then it gets pumped out to those spokes into the deepest part of the lake where it's needed the most. And that kind of northwestern area of the lake, northeastern area of the lake is the deepest part and where the most nutrient-laden sediment is. So that's where it's needed the most. How do we evaluate all these things? So we had a number of different experts we brought on board to help evaluate this. I already mentioned Dr. Alex Horn from Berkeley, UC Berkeley. We have Dr. Michael Anderson. Both of these guys have worked on Lake Elsinore for almost their entire careers. They've been out forever. Dr. Anderson's from UC Riverside. Of course, we have people from our team, Chris and myself, as well as some other of our certified lake managers that are other parts of the company. And then we had people from PACE that actually would help design the system. Andy and Evan helped us to kind of evaluate the system. I'll show you how we came up with a system for this. So first we just came up with, okay, let's take these systems all, the different types of dissolution systems, the different type of technologies. What are the pros and cons of these various systems? I'm not going to walk through all of this, but just for example, like the shoreline system. Well, it's easy to access because it's right there on the shore. If you need any maintenance, it's right there. You can just take it apart, fix it. The downside is it requires really long, lengthy pipes, and it requires a lot of pumping. If you have to pump water up and out of the lake and then back to the lake, it's a lot more energy intensive than it was, say, for submerged. You don't have that head pressure. You don't have to pump the water up out of the lake. It just stays in the lake the whole time. And so we just, kind of talked through the various and thought through the various different pros and cons of each of the different technologies. And then, the next slide, we came up with a rating system. And so it's a lot of numbers here, but I'll try to make it easy for you. This is showing the various different technologies, the dissolution technology we have on the right, their capital costs, and then we had a rating system. And you can see the various, I'm sorry, the formatting's a little messed up again, but we had six different rating things that we rated them on. For example, cost, reliability, ease of construction, O&M, social, political, aesthetic value, sustainability and other benefits, miscellaneous benefits. And we were rating all these, and each of them were weighted. So you can see that like a 30%. That means we weighted these costs. The cost was the most important factor, followed by regulatory compliance would be 25% weight. And then reliability, is it actually going to work for long term? 20% weight. And so we weighted all these factors. Each of us independently scored. So taking the mean of all the different experts, come up with an overall score. It turned out that numbers 2 and number 4, so it's the liquid oxygen system, either through a submerged spoke or through this two-stream crib spoke system, were the two that we decided scored the best, kind of taking all of our scores together. And so looking at those a bit further, now that's just the delivery system. Now what type of technology? So we took each of those, the LOX crib or the LOX submerged, and look at the two different technologies, whether a species cone or the oxygen saturation technology or the blue and green, and rated each of those separately based on each of the systems. In the end, it came out that the species cone was the one that actually ended up as the most relevant, scoring a 4.2 and a 4.1 average score, weighted score. So those are the two that at this point we're kind of moving forward with as a recommendation. We're still in the evaluation process of which of those two we're actually going to recommend as the final choice for that. These are the loads that we're trying to remove. So we have the internal load of the recycled water coming to the lake that we need to account for, as well as the external loads coming in from the watershed and any sort of internal recycling going on the lake. But the total load that we need to reduce, it's right in the middle where you can't see it. 45, I believe it's 1,000 kilograms per year, and about 3,500 kilograms per year, I believe is what that says in the middle there. If we were to keep oxygen elevated in the bottom waters by using whatever technology we decide is the recommendation, we would be able to reduce about 51,000 kilograms per year of nitrogen and about 11,000 kilograms per year of phosphorus, which is well over the target. As you can see, we're well over for the phosphorus target, and we're just barely above where we are for nitrogen. So the little bullet out there to the side kind of says, well, in the future, we're probably going to need to add something additional to get nitrogen over the edge. But that's where we stand right now. And I think this is my last slide. Yeah, so just kind of where we are now. So we put out a report for this evaluation process for Lake Elsinore last year. Went through a comment process. We responded to those comments. Did some scientific studies looking at the SOD, again, talking about how much oxygen do we really need to deliver to make this worthwhile. And then finally, we've got the Moliere system now that the city is really pushing forward. It's showing a lot of benefits. Okay, how does that get incorporated now? Because before, when we did this whole evaluation study, the Moliere pilot project hadn't even started yet. So now that we're seeing some of the benefits of this nanobubble system, how does that get incorporated into the final design of what we were going to be moving forward with? That's still in discussion. And then we'll be moving on to the procurement process of all of those things, and from there. And hopefully, this is a process that takes a while to make sure we're collecting the right data and getting the right decisions made and getting the right people in the room to talk about it. But that's kind of where we stand right now. And so, yeah, I think that was it. So take any questions.